At the dawn of the machine age, a new kind of titan began to rise in factories across the world. Giant hydraulic forging presses. Some were so large, they made grown men look like mini action figures beside them, towering as high as 8 stories tall and anchored deep into the concrete and bedrock. They didn't feel like machines. They felt like buildings. In a single stroke, they could drive incredible force into the red-hot steel. As the workers stood only a few steps away, they could feel the heat and the vibration through the floor. But when the press started to close, there was no warning signal and no way to stop it. Only a few feet and a few seconds separated the men from thousands of tons of crushing force. This is the story of the hydraulic forging press giants. Fortunes were made, lives were crushed, and their surprising role in the Cold War helped shape the world that followed. To understand why the press was even built, you have to start with the failures that no one else could see. In the mid-1800s, factories faced limits that their existing tools could not solve. Steel parts were getting thicker and larger, but the old existing methods only worked on the surface, which ultimately left hidden flaws that would eventually show up later on. Steam hammers were powerful but not consistent. They shook entire buildings and tired out the workers nearby. And even after countless blows, cracks from the hammer strikes could still form deep inside the rails. Artillery and ship parts setting up failures that arrived after the work was already considered to be finished. That problem forced a different kind of thinking. In 1795, Joseph Bramah proposed a new idea, using liquid pressure rather than impact to apply force. The point wasn't just power. There was control, allowing pressure to be applied evenly and steadily, instead of through repeated hits. And in the 1860s, engineers like John Haswell started using this idea for forging. One steady press could drive heat and pressure through an entire steel block, enhancing the internal structure instead of only shaping the outside. This change happened out of necessity. Not just for improvement, railroads were expanding. Artillery was growing heavier. Ships were getting larger, and the demand was for parts with fewer hidden flaws and less wasted material. Speaking of necessity and improvement, if these kind of industrial stories are something that you enjoy, I'd be truly grateful if you could subscribe and let me know in the comments what kind of stories or disasters that I should investigate next. Now let's get back to the action. Early forging. Presses could apply several thousand tons of force. In one controlled motion, they reduced extra machining, they cut waste, and they made parts more reliable, giving factory owners a practical way to keep up with the demand. But they also created a new kind of risk, because this time, the force didn't arrive as blows that you could anticipate, like that of a steam hammer. Instead, it arrived as one continuous closing motion, and once it started, it didn't stop. And that single change rewrote the forge floor, because the violence didn't vanish. It just became more controlled. By the 1880s, that control was no longer an idea. It was steel, concrete, and pressure, all scaled to industrial size. Forge shops had machines larger than the buildings themselves. Steam hammers weighing more than 1,000 tons ran day and night, cracking walls, loosening bolts, and placing constant strain on the men who worked beside them. The hydraulic forging press marked a clear break from that approach. It didn't rely on repeated impacts. Instead, it pressed down in a steady, controlled motion made from enormous steel castings, some weighing hundreds of tons. The press itself needed special equipment just to assemble it. Now the force came from pressure and not just movement. Hydraulic systems stored energy inside sealed cylinders, building up thousands of pounds per square inch before anything moved. And when that pressure was released, it acted evenly without the shock or the noise of a hammer blow. One single press stroke could do the work of dozens of hammer impacts, shaping a hot steel block in one smooth action. By the late 1800s, Some factories eliminated entire rows of hammers, making forgings with fewer hidden flaws and far less waste. But this method brought new risks. In cold weather or under heavy loads, hydraulic systems could freeze or get stuck. Workers were sometimes forced to heat pipes, loosen fittings, or work near stored pressure that had not yet been released. As the era of hammering receded, forge floors undoubtedly grew more tranquil, yet the emerging hazards were far more elusive to detect. The energy was no longer abrupt or clamorous. Rather, it was unrelenting and obscured, exerting itself mutely within environments, engineered around thousands of tons of steel and latent power. And once industrial plants committed to that level of force, they were faced with a task even more arduous than constructing the machine. They had to engineer the very substrate beneath it. The apparatus wasn't merely placed within a facility. The entire plant essentially had to be reconstructed as a foundation. By the dawn of the 20th century, the primary obstacle wasn't solely the fabrication of the press, but maintaining its equilibrium once fully erected. The sheer mass rendered standard factory decks inadequate. Consequently, the initial labor required no craft at all. It was pure excavation. Constructors were forced to dig profound foundations before fitting any major components. Certain units towered over 80 feet above the deck, with an additional 30 feet submerged below the surface. That wasn't a case of excessive engineering. It was the baseline necessity for structural steadiness. These subterranean sections were embedded in concrete and solid rock. Since lighter bases could not sustain the frame, once the load was engaged, manufactories had no alternative but to conform to this. In numerous instances, the press became the focal point around which the whole site was devised, with enclosures, hoists, and energy networks configured to sustain a single, immovable machine. The structure didn't merely contain the press. The structure was built to feed its requirements. Structural soundness relied on gargantuan vertical pillars, each as broad as an ancient tree, and more elongated than most domestic dwellings. Wrought from alloyed steel, these pillars underwent heat treatment in kilns, stretching beyond 100 feet in length, to guarantee they could endure prolonged loads without fracturing. Yet a solitary blunder meant the entire assembly could collapse. Thus, meticulousness was mandatory for every phase. A defect masked in one pillar could distort frames, shatter foundations, or redirect force into zones not designed to resist it. And the terrifying aspect was that you wouldn't always be aware until the press finally engaged a maximum load. And as for the workforce, well, you can appreciate that they recognized the perils early on. They observed as hundreds of tons of liquefied steel were decanted into molds, aware that the engine being forged would soon command the environment and challenge the very substrate of the earth. The machine wasn't merely installed on a plot, it was irrevocably moored to the planet, a requirement dictated by its magnitude, not by preference. Once it was established, all that ensued had to coexist with it, including the staff. And when the Titans finally stood tall, the subsequent inquiry wasn't whether they functioned, it was determining who was permitted to command them. By the 1950s, this magnitude was no longer a prototype. It was fully functional and governed by a human touch. Command within the forge had been distilled to a single point. At sites like Air Force Plant 47 Inches Cleveland, one operative remained at the steering of a machine, capable of energies that no human frame could survive. The control apparatus appeared elementary. Engineers later remarked that the press reacts instantaneously and with precision to the solitary operator's touch, on a handle a mere 3 inches in length, and that was the disquieting aspect. This demonstrates how minimal effort was needed to govern such immense power. That minute shift directed a network capable of exerting up to 50,000 tons of force. Wu Wan, Surrounding it were colossally sized components, fasteners over 50 inches wide, some exceeding 50 tons in mass, and individual pieces weightier than entire workshops from the 19th century. Proportions of that nature redefine what is considered typical. Once the compression initiated, it was impossible to halt. The press advanced relentlessly, compacting heated steel as staff observed from a secure perimeter. It didn't strike. It didn't roar. It simply continued to close. Right. Tell me, do you have any background in operating or laboring around these magnificent machines? If you do, please inform me in the comments section so we can acknowledge the true protagonists of this narrative. The operative didn't require physical strength to command the press. He steered it, placing faith in every regulator, seal, and casting to function as intended so he could maintain mastery. But the system was indifferent to his assurance. It was concerned solely with tolerances. So, within the press hall, the silence was conspicuous. Thousands of tons shifted at the movement of a tiny 3-inch handle, and every person was aware of how narrowly things could spiral out of mastery. And if a component failed, it wouldn't fail boisterously at the outset. It would fail mutely until there was no leeway left for movement. But the operative wasn't the individual in the greatest proximity to the peril. The men in closest reach were those who were required to step beneath it. The handle governed the magnitude. The deck hands existed within its rhythm. The most perilous sight in the workshop was no longer the kiln. Rather, it was the zone directly beneath the machinery. When the molds were parted, the void could exceed 15 feet, and the tether below was as elongated as a locomotive carriage. It appeared spacious, but in practice it functioned as a snare. Within that zone, laborers positioned glowing steel, utilizing manual cues whilst bellowing directions. They stood mere paces from the die surfaces, aware that once the compression commenced, there was no viable means of retreat or cessation. They weren't merely observing an engine. They were synchronizing with it as though their existence relied upon it. The labor adhered to a rigid protocol. Steel was scorched, compressed, retempered and compressed once more, occasionally numerous times for a single project. Pumps charged the reservoirs. Regulators were verified, and every phase had to occur in precise sequence to maintain mastery over the process. And the protocol only seemed secure because it was customary. This meticulous cooperation was as vital for welfare as it was for task completion. Yet the tolerance was slim. One synchronization error could ensnare a limb, an implement, or even an entire worker between moving elements that would not halt, regardless of the circumstances. Once initiated, it concluded. A verbal account from Bethlehem Steel subsequently summarized the state of affairs. A welfare supervisor remarked that protection policies only functioned when directorship endorsed them. Otherwise, they were merely rhetoric. Whilst staff persisted in confronting hazardous circumstances because the machine did not dither, only the production timelines did. The apparatus was indifferent to an individual's proficiency. It functioned solely according to displacement and energy. To toil securely beneath the molds, laborers had to abide by methods, interact articulately, and believe that the mechanisms would operate as intended. And belief was the most tenuous element of the entire arrangement. When the press retracted, everything returned to stillness. Staff anticipated its opening, ensuring the sequence had concluded as required, as the subsequent motion was invariably the same. Re-enter the zone, align it, and hope no variables had shifted. And yet, even with that degree of peril, the market didn't decelerate. It intensified, because once the sector witnessed what these units could achieve, it craved even more massive components. As directors across various sectors grasped the capabilities of large forging units, workshops became less hesitant. Numerous industries began transitioning, prioritizing the fabrication of larger, more rigorous components that legacy forging practices could no longer manage. The presses didn't merely refine output, they quite literally redefined the standard of normalcy. Aeronautics was among the primary sectors to adopt this change. Press-forged parts distributed tension along their internal fiber structure, thus they could flex under load without fracturing. By the 1930s, aircraft constructors were requisitioning forgings, weighing tens of thousands of pounds, prior to finishing, which only immense presses could manufacture. And once a blueprint relies on a solitary forging, the forged piece becomes essential. That reliance swiftly conditioned the remainder of the output chain. Once an airframe was conceived around a massive forging, the constructor cannot simply alternate for smaller components. Without complete revision, revalidation, and new instrumentation, the machine didn't just create the component, it mandated the architecture, the timeline, and the entire logistical network behind it. Merchant naval construction and heavy production adhered to a comparable trend. Massive units sustained vital components that thrived with fewer connections, fewer bolts, and fewer distinct segments that could loosen or fail under cyclical tension. Over time, firms capitalized on press potential because it diminished remanufacturing, reduced waste, and lowered the quantity of milling stages required to achieve final proportions. But every gain in productivity involved a compromise. Fewer substitutes when the apparatus was inoperative. As more sectors integrated press-forged elements, the market coalesced around a handful of sites that could provide them. By the mid-1950s, Air Force Plant 47 inches Cleveland and Air Force Plant 63 inches North Grafton were among the scarce locations with 50,000-ton units, capable of fabricating the massive forgings that commercial manufacturers were now engineering around. In the commercial sector, the press was not a figurehead. It was an absolute necessity, and once that necessity is established, the subsequent inquiry isn't how we construct larger, it's what occurs when the machine arrests, or when the energy intended for containment escapes. The primary hazard in a forging workshop is not the temperature, but a concealed energy. A hydraulic unit may appear motionless. It can retain sufficient tension to distort steel and inflict fatal trauma. It can technically be deactivated whilst remaining fully charged. During the decades between the Great Wars, workshops housing massive units grew more vigilant during operational pauses. Pumping networks could accumulate and sustain approximately 4,500 psi of tension within fortified conduits, sequestering power behind regulators and gaskets, which provided no indication prior to a breach. And the peril didn't lie in the kinetic motion you could observe. It was the atmospheric pressure that you couldn't. The perimeter surrounding the machine was perpetually hazardous. Certain immense units featured die platforms, roughly 12 by 26 feet, sufficiently large to draw staff inward while offering no margin for error. Once the unit commenced its descent, it persisted regardless of the proximity or exhaustion of the personnel. The apparatus didn't gauge the atmosphere. It merely executed the sequence. Casualty documentation from safety authorities reveals a consistent trend. Laborers were pulverized whilst performing mundane duties, such as extracting scrap, aligning feedstock, or making refinements. These chores turned lethal when sequestered energy was discharged, or the machinery spontaneously resumed its descent. And as you might have surmised, these events didn't occur during the climactic phases. They transpired during the commonplace ones. Inquiries attributed blame to factors like omitted protocols, inadequate shielding, or mechanical malfunctions, yet the consequence was invariably identical. The gap vanished and time was exhausted. With a steam-driven hammer, it generates significant noise and vibration, so you are cognizant of its operation, but a press advances with virtually no preamble. It functions with a deliberate and steady pace, and once it engages, it persists until completion. That is what renders it so illusory. It does not feel critical until it is already catastrophic, and that is what the documentation cannot entirely encapsulate. The sensation of toiling beside an engine that could be lethal, even whilst appearing placid. The statistics elucidated the trend, but it was the staff who explained the resolve to return regardless. The men operating these engines grasped their inherent volatility. Nevertheless, they reported for duty daily, fully cognizant of the dangers, not because the hazard was imperceptible, but because it was customary. At establishments like Bethlehem Steel, the workforce felt both gratification and a perpetual awareness of peril. One worker remarked, "I was immensely pleased to labor at Bethlehem Steel. I relished the vocation." And this gratification intensified. In a climate where blunders could have grave repercussions, in the mid-20th century, certain smelting plants employed tens of thousands of staff, all aware that the machine would grant no exemptions to anyone. The mandate was straightforward. The unit was indifferent to your status. Servicing a massive forging press was not mere routine drudgery. It required years of proficiency and mentorship from seniors. Workers noted the machinery was hushed and disciplined, but it was never charitable. A former operative recalled how distinct the press was from legacy hardware, characterizing it as serene and uneventful compared to steam-powered hammers. The apparent lack of effort is uncanny. The machine's seamless movement underscored its formidable energy. Not that it was any less treacherous. If anything, the tranquility made it simpler to overlook the power stored within the iron. Decades later, directors and overseers still spoke of the expertise and fidelity of the forge teams, describing them as proficient, steadfast, and honored by their trade. The role necessitated meticulous coordination and adherence to methods, not merely physical brawn. In that hall, discipline outweighed bravado. The machine didn't compensate the reckless. It functioned best for those who were methodical and unwavering, for laborers who learned to honor these boundaries. Concluding each shift unharmed became a badge of professionalism throughout their tenure. It was departing the premises at the day's end. The genuine triumph was not the contouring of alloy, yet pride didn't render the labor secure. Welfare measures arrived later. After the casualties accumulated and the justifications were exhausted, forging presses were engineered for dominance, not protection. Most of the safeguards that were eventually implemented emerged only following disasters, and the injuries demonstrated their necessity beyond doubt. In other words, the regulatory code was written in blood. Throughout the majority of the early 20th century, output quotas superseded welfare concerns. Protective barriers were sparse, methods were vaguely established, and the onus for secure operation frequently lay with foremen, who relied on intuition rather than formalized instruction. That strategy sufficed until it didn't. At facilities like Bethlehem Steel, the frequency of injuries mounted over time. Numerous reports actually portrayed workers who recognized the perils, but also understood they were mandated to sustain production levels. To be sure, welfare briefings were conducted, yet they lacked consistent endorsement from the executive tier. Consequently, they yielded little influence when delivery targets loomed. When the timetable compressed, the safety buffers were the first to vanish. A welfare supervisor articulated it plainly. It may require slightly more duration to proceed securely, but you shall be far superior to the fellow who does not. This observation was forged from grim experience. Not extracted from an instructional pamphlet, it was counsel funded by the trauma of predecessors. Throughout the 1940s and 1950s, corporations began implementing physical obstructions, isolation protocols, and more stringent regulations for upkeep and calibration. These modifications frequently hampered output speed, occasionally subtly, at other times significantly, and the workforce didn't always embrace them immediately. For every safeguard served as a tacit confession. The previous methodology had been exacted in human lives. Notwithstanding these advancements, the presses remained inherently treacherous. There was no circumvention for that reality. These engines could discharge tens of thousands of tons of energy, and they could never be rendered entirely benign, merely less volatile. Adhering to welfare codes was imperative, as violating them persisted in resulting in catastrophic mishaps. It didn't merely penalize the foolhardy, it penalized anyone who found themselves in proximity. The welfare standards that eventually became universal were not established as a measure of foresight. They were integrated only after individuals had suffered grievous harm, surrounding machines that had long proven their lethal potential. And even then, the hardware remained unchanged. Only the governance surrounding it evolved. But then the gravity of the situation shifted once more, because these were no longer merely workshop regulations. They transitioned into matters of sovereign importance. The influence of these gargantuan engines swiftly transcended the boundaries of mere commercial utility. Once states grasped the capabilities of massive forging presses, the machinery was deemed vital for far more than manufacturing alone. They became assets of strategic significance after the Second World War. Analysts scrutinizing seized German aeronautical technology, observed a definitive pattern. The primary forged components were lighter, more robust, and more consistent than comparable Allied parts, as they were fabricated as monolithic pieces, rather than assembled from multiple bonded sections. It transpired that this was conventional doctrine for the Germans, and it implied a disquieting reality. Superior aviation could emerge from different corners of the globe, equipped with more formidable presses. These revelations sparked immediate trepidation. Intelligence reports soon indicated that the Soviet Union had requisitioned Germany's most substantial forging units, including machines capable of exerting tens of thousands of tons of pressure. To American authorities, this represented a seismic shift in industrial hegemony, not merely a transfer of physical hardware. Consequently, in the early 1950s, the United States inaugurated the heavy press program. The crown jewel was a closed-die forging press, with a 50,000-ton specification, constructed at Air Force Plant 47 inches Cleveland and commissioned in 1955. The objective was not rapid throughput, but rather a controlled, sovereign capability, the capacity to fabricate the most massive aeronautical components on demand. These units could contour aluminum and steel billets, exceeding 200,000 pounds in mass, prior to any milling. The completed components were destined for heavy bombers, logistical transports, and avant-garde aircraft still in the conceptual phase. To put it another way, the machine was being engineered for vessels that did not yet exist. By virtue of this, the press itself became a cornerstone of national defense strategy, and its operational uptime sustained entire air fleets. And should it fail, strategic capability failed alongside it. But by that juncture, forging presses were no longer mere workshop tools. They had quietly evolved into critical military infrastructure, producing parts that dictated an aircraft's range, its payload capacity, and its operational endurance. Unobtrusively, the forge became the front line of defense, and unlike jet fighters or munitions, these machines were never deployed. They remained stationary, anchored, permanent, and vigilant. That permanence is the final, peculiar truth of the forging press. It was engineered to reshape metal, yet it can never relocate itself. Long after the laborers who cast its foundations grew weary or passed, the presses remained exactly where they were initially commissioned. Edifices were erected around them, and the configuration of every workshop was dictated by engines that were never intended for transit. They didn't merely outlive the men, they outlasted the epoch. Each unit was composed of titanic sections. Its skeleton utilized colossal steel castings, occasionally so immense that an entire smelting works was required to produce a single component. These parts were fashioned to endure for half a century, not for frequent replacement. Once the steel was established, it was destined to remain so. Occupational habits evolved to accommodate this sense of fixity. In certain plants, the press determined the placement of walls, the trajectory of gantry cranes, and the zones of safe human passage. The facility was required to conform to the machine, demonstrating the constraints imposed by its mass and its fixed coordinates. The press did not occupy the building. The building learned to accommodate the press. Modern operators remark that their experiences mirror those of their predecessors. The units still react with fluid precision to their commands, closing with deliberation and demanding the same vigilance and reverence as of old. The steering may appear effortless, but the consequences never were. These engines are more hushed today than the legacy forging techniques. They still advance with slow, meticulous caution, and those toiling in the vicinity remain guarded, cognizant that the identical motion can still contour metal or inflict grievous injury. The peril hasn't vanished. It has simply learned the art of silence.